Good morning, everyone. My name is Dhanraju Vatina, working as an assistant professor in the Department of Electronics and Communication Engineering. Welcome to the Microwave Engineering Laboratory. See, the list of experiments in the Microwave Engineering Laboratory is the first one, reflex klystron characteristics, and second one, gun diode characteristics, and third, attenuation measurement, and fourth experiment is directional coupler characteristics, fifth, scattering parameters of circulator, sixth experiment is scattering parameters of E-plane T, and seventh one, scattering parameters of H-plane T. Eighth experiment is scattering parameters of magic T. And ninth one, voltage standing wave ratio measurement of open and short circuit loads. 10th one, voltage standing wave ratio measurement of matched load. And 11th one, measurement of impedance of a given load. And 12th experiment is microwave frequency and wavelength measurement. And today's experiment is to determine frequency and wavelength of rectangular waveguide operated in a fundamental mode that we used to call it like a TE10 mode. Required operators: microwave source, klystron tube, isolator, frequency meter, variable attenuator, slotted line, tunable probe, detector mount. And matched termination, klystron power supply and klystron mount, cooling fan, cables, and voltage standing wave ratio measurement equipment or CRO. So these are the required operators which we used in the microwave laboratory, that too particularly to do the experiment. Let's see the block diagram. The first block, microwave test bench, is the first one, microwave source, and source is connected to the isolator, isolator to the variable attenuator, variable attenuator to the frequency meter to slotted line to the matched load to the VSWR meter or CRO. So microwave source. So initially, so there is a klystron power supply to klystron mount. So when you switch on the klystron power supply, so klystron power supply is a solid state regulated power supply. So by using that solid state power supply, so we have to apply a particular voltage to klystron mount. And klystron power supply incorporates different knobs. So one is gun bias knob, voltage knob, and second one is Rippler voltage knob. So by rotating the gun bias voltage knob, so we have to fix the voltage, beam voltage, 230 to 240, in between 230 to 240. Okay. So after fixing the voltage, we have to take down the beam current reading, and always remember that beam current should not exceed 18 milliamps. Should not exceed 18 milliamps. After that, so rotate the knob to the Rippler. Okay. By rotating the Rippler voltage knob in anti-clockwise direction, okay, you have to see the maximum signal strength on CRO. Okay, we have to fix the, by rotating the Rippler knob, we have to fix the maximum signal strength appears at CRO. Okay, so klystron power supply to connection is to klystron mount, right? So when you apply a voltage to the klystron mount, so klystron mount is when you energize the klystron mount, it fires a huge amount of electrons inside the tube, and when there is a movement of electron that representing the energy, when the energy is passing through the transmission line, that we noted like a microwave energy. So microwave energy is generated by the klystron tube, and that energy is passes through the isolator. Here the purpose of the isolator is it redirects the energy into a particular direction, only one direction, or to forward direction. So microwave energy passes through the isolator to the variable attenuator. So here there is some sort of attenuation of the signal exists, then variable attenuator to the frequency meter. And by rotating the frequency meter, okay, we can fix a particular frequency to the energy. I mean, here the band value is 8.2 to 12.4, right? So in between, so by rotating this frequency meter, we can allot a particular frequency to the microwave energy generated by the klystron mount. Then after that, that moves to the slotted line. Then by moving the slotted line on the section, so we can calculate the distance values, minimum distance values D1 and D2. So by calculating the D1 and the D2 values, we can find out the wavelength of the microwave energy. So purpose of the slotted line is we can calculate the minimum distance value or double minimum points. I'll explain clearly about the double minimum points while we doing the voltage standing wave ratio calculations. That is another experiment in the microwave engineering laboratory. So I'll explain later regarding the purpose of the slotted line clearly. Then after that, matched load or termination, then voltage standing wave ratio and CRO. Okay. So by using a detector mount, we can see the signal on CRO or VSWR meter. So this is what the microwave test bench what we are using in the microwave engineering laboratory. Coming to the calculation part, so initially we have to calculate the guided wavelength. The formula for the guided wavelength lambda g equal to 2 into d2 minus d1. So I told now, so by moving the slotted section, okay, left to right, we can calculate the two minimum points, that is two minimum distances, so d1 and d2. Okay, so by calculating the distances, simply you can substitute those values in the formula. So lambda g equal to 2 into d2 minus d1 centimeters. By substituting those values, we can find out the guided wavelength in centimeters. Okay, then lambda g equal to lambda naught divided by square root of 1 minus lambda naught divided by lambda c whole square. Here lambda c is a cutoff wavelength. Okay, then lambda c cutoff wavelength equal to 2 into a, that is a dimension of the rectangular waveguide, that is a fixed value. Okay, by substitute that value, we can find out the lambda c. So we know lambda c and lambda g. Substituting lambda c and lambda g in the above formula, we can find out the wavelength. So we know lambda naught and c, that is a relative velocity, right? That is a 3 into 10 power 10 in centimeters. By substituting c value and lambda naught, we can simply find out the frequency of the microwave signal. So this is how we need to find out the frequency and the wavelength of the signals or microwave signal in the laboratory. Let's coming to the Viva questions in this particular experiment. The first question is indicate the frequency versus wavelength for the X band. So X band we are using in the laboratory, right? So indicate the frequency versus wavelength for the X band. And second question is explain the principle of isolator and circulator. And third question is principle of frequency meter. And fourth question is what type of frequency meter used in the microwave test bench. And last question is what is a microwave frequency range. So these are the 5 questions I am giving now. So just try to answer these questions. Okay, thank you. Now let's move to the laboratory. We'll perform the experiment and we'll see the experiment practically. Then I'll explain the calculations on board again. Thank you so much. Let's move on to the laboratory. Good morning, students. Welcome back to the microwave engineering laboratory. And today's experiment is microwave frequency and wavelength measurements. switch on the cooling fan. So whenever you are in the laboratory, make sure the first step is you have to switch on the cooling fan and make sure the air flow towards to the mount, because it is a high power generator. So to cool down this one, we are using the cooling fan. And next, switch on the Klystron power supply. The Klystron power supply is a solid state regulated power supply, and it incorporates different sections. I mean modulation section, display section, and display unit, beam voltage knob, Rippler voltage knob, and modulation function knobs. And here modulation function knobs, make sure keep it mid position. And now select the modulation as a AM modulation. Select the modulation as a AM. And now by rotating the beam voltage knob, fix the beam voltage in between 230 to 240. Fix the voltage 230 to 240. Write down the beam voltage. Beam voltage is now 235. Beam voltage is 235 volts. And now go to current. Take the beam current. Beam current is 17 milliamps. 17 milliamps. And now by rotating the Rippler knob, by rotating the Rippler voltage knob in anti-clockwise direction, just check it here. So where you go getting the maximum signal, you have to verify it by rotating the Rippler voltage knob completely and check it. Wherever you find the maximum signal strength on CRO, and you fix that voltage. And now we are taking 201 is a Rippler voltage, and make sure, so keep a minus sign because it is a reverse voltage. Rippler, no? Yeah. So Rippler voltage is minus 201. Yeah. And after applying the voltage, beam voltage to the Klystron mount, and it is connected to a isolator, isolated to variable attenuator to frequency meter, and detector mount. And here the purpose of the mount is, when you apply a voltage to a mount, it fires the electron inside the tube, okay, and those electrons moves like a free electrons through the waveguide structure. When the electrons are moving, it creates the charge, and the charge is moving towards to the transmission line, and obviously there is an electromagnetic field, means microwave energy is generated by the tube, and that energy travel towards to the isolator. And the purpose of isolator is it sends the, or it allows the energy in only one direction, that means in forward direction only. Then after isolator, energy reaches to the attenuator, variable attenuator. After variable attenuator, there is a frequency meter. By using this frequency meter, by rotating the frequency meter, we can allot, or we can give a particular frequency to a microwave energy, and that energy is detected by the detector mount. And the purpose of the detector mount is it detects the low frequency microwave signals, and that you can see by using the oscilloscope. Let's see. And today's experiment is microwave frequency measurement, right? So now whatever the energy generated by the tube, which is passing through the transmission line, for that energy you have to allot a particular frequency to a energy. And here the frequency meter having a band 8.2 to 12.4. So this is what the microwave frequency band. In this particular band, you have to allot a particular frequency, exact frequency to a energy.
So let me rotate the frequency meter slowly, and at a particular point, particular point, so you will observe a dip in the signal. So wherever you feels the dip, and that is what the frequency of this microwave energy. See, observe carefully. So let me rotate the frequency meter slowly. You have to perform the experiment. This one very slowly. Okay. Rotate the frequency meter. So when you are rotating the frequency meter, have a eye on oscilloscope, on the signal. See here, check it clearly. Yeah. See, there is a dip, right? Yeah. This is what the required frequency. Just keep it like this and see the frequency. And frequency meter contains, there are two strip lines, copper strip lines, and there is a red indication line in between the two strip lines, and there is a red line, right? So there is a scale. So in between, whatever the reading shows, red line shows, that is what the reading we need. So here the reading is 9.68. Exactly, yeah. Write down. The frequency is 9.68. Okay, we know the frequency, right? So by knowing the frequency, we can calculate the wavelength. So we know the formula. The wavelength lambda equal to wavelength, write in the formula, the wavelength lambda equal to C by F, and we know the value, C value, so 3 into 10 power 8, substitute that value, and we already know the frequency, we calculated practically right now. So by substituting the frequency and the C values, and you will get the wavelength of the microwave signal. This is what the experiment. Okay, so after taking the frequency, just keep it as it is. Take down the readings, make it down, and now change the display section to the beam, regular, current and beam. Now reduce the beam voltage to 0, take down, okay, then rotate the regular voltage now and check the signal, make it be like a 0, okay. Perform all the things, and now switch off the power supply. Okay, and check it. If you still feel the heat, just leave the fan for a while. So after 2 or 3 minutes, just switch off the fan also. So this is how you need to do the experiment in the microwave laboratory. Thank you so much. We are coming to the calculation part. So practically we have taken the observations. The first observation is beam voltage 235 volts, and second observation beam current 18 milliamps, and regular voltage is 201. So it is a reverse direction, right? That's why I have taken the minus sign. So minus 201. Step 2, frequency calculation using the frequency meter, that we have found 9.68 gigahertz by rotating the frequency meter. So we have calculated the frequency of the signal is 9.68 gigahertz. So we know the frequency, right? So step number 3, you have to calculate the wavelength of the signal. So experiment is to determine frequency and wavelength of the microwave signal, rectangular waveguide operated in a TE10 mode. This is a fundamental mode. So you know about clearly what about the fundamental mode and operations and all in the regular class. Now you have to calculate the wavelength by using the frequency. We know the formula. the wavelength of the signal lambda equal to c by f. So relative velocity of the signal by frequency of the signal. So the relative velocity we know, so 3 into 10 power 8, that is in 10 power 8 or 10 power 10 in meters we can take. So 3 into 10 power 10 divided by the frequency value is 9.68, right? So 9.68 gigahertz. So 10 power 9. Okay. So the value is 3.09 centimeters. So finally we have found frequency and wavelength both. So this is how you have to perform the experiment, microwave frequency and wavelength measurement. In another way, so in reverse direction also we can find out the frequency. First you have to find out the wavelength, and by knowing the wavelength we can find out the frequency also. So I will show the first how to calculate the wavelength. By knowing the wavelength, how to calculate the frequency also in reverse order. Yeah, we can find out the frequency in the reverse order. So in previous we have found out the frequency directly. From the frequency, or by using the frequency, then we calculate the lambda, I mean wavelength of the signal. But here in reverse order, so initially you have to find out the wavelength. By knowing the wavelength, how to find out the frequency, we'll see now. So for this one, you have to use the one more section in the microwave test bench, that is a slotted line that we used to do, that we will use in the microwave that we used to find out the voltage standing wave ratio experiment. So while you doing the voltage standing wave ratio experiment, I'll explain how to take these values and how to calculate the wavelength and frequency also. But now just see, initially we have to find out the distance values in D1 and D2 by moving the slotted section. So by performing that, the D1 value is 10.1 centimeters and D2 value is 12.3 centimeters. By knowing the D1 and D2 values, we can find out the guided wavelength. So the formula for the guided wavelength is lambda g equal to 2 into D2 minus D1. Okay, now substitute the values here. So 2 into D2 value 12 minus 3 and 12.3 minus 10.1. So by substituting the values, we will get the value is guided wavelength is 4.4. And next cutoff wavelength. So lambda c equal to 2 into a, and this is not the fixed value. Okay. So 2 into a, 2 into 2.286. This is a predefined value. Okay, 2 into 2.286 gives the 4.572. So we know the guided wavelength as well as the cutoff wavelength. So by knowing these things, we can find out the lambda naught. So lambda g is equal to lambda naught divided by square root of 1 minus lambda naught by lambda c whole square. Substitute those values and you will get the lambda naught value is 3.17. Okay. So by knowing this wavelength of the microwave signal, how to find out the frequency? We know the relation frequency, which is equal to c divided by lambda naught, relative velocity of the signal to wavelength, right? So substitute c and lambda naught values. So f equal to 3 into 10 power 10 divided by 3.17. By substituting and perform the calculations, you will get the frequency value is 9.4 gigahertz. Previously in the laboratory we found the value is 9.6, but here 9.4. So whenever you are doing the experiments in the microwave laboratory, you will always find out these minute changes. Okay, so which is very near to the whatever we found out in the practically. So we can consider it. Yeah, we can consider this value. So this is how we can find out the microwave frequency and wavelength measurements. Thank you so much.